Welcome friends to this first session of fluid mechanics and rate processes. I would like to speak to you today about the course and the excitement in this course that we are going to see for the rest of the semester. So, I would first like to tell you what is the purpose of this course. When we look at fluid mechanics, we would like to look at the engineering aspects of fluid mechanics, and you would see that there are three aspects that we would be looking at as far as this course is concerned. One is that if there is a fluid flow across an object, it exerts forces. Okay? The other is that if you want to move a object through a fluid, then you need to exert some energy or some force on it. So, you would like to estimate as an engineer what kind of energy that you need to put into the object. And then the other aspect is the modification of the fluid flow with respect to the heat and vapor transfer. And as an example, you can see the desert cooler or the evaporative cooler, wherein I am sure many of you have used this in the summer time, where there is a fan and you would like to absorb the humidity of the air to cool the temperature of the hot air. So, there is a breeze that is sucked in. So, you put in energy, there is water inside this cooler, and there is a pump which kind of sprays the water at the side screens, and then when the air is blown, it is sucked from the outside through the side screens, and then you get a cool stream. So, you can see there is all these coming into action, including the heat transfer and the vapor transfer. I would like to give you some more examples of the fascinating aspects of fluid flow. For example, a dam. You know, most of the electricity that we get is produced by some kind of machines, and here in this case is hydroelectricity, which is produced by storing water in a dam, and then as the water spills out of this dam, you would like to extract energy out of it, maybe through some turbines and so on. Now, the construction of a dam is very interesting. So, those of you who are civil engineers or for that matter engineers and scientists in general, you would notice that you use these two sides which are kind of banked by rocky structures like mountains, hills, and then there is this, you want to put a barrier to the water, and because this water is going to exert enormous pressure, so this wall kind of structure which holds the water has to be extremely strong. So, as an engineer, you would like to estimate what is the force, what is the moment on the structure, so that you can design it properly and there is no catastrophe. In fact, what happens as the river, as the life of the dam increases, the river carries the silt, and you would get all kinds of things happening in it, you know, environmental issues. Sometimes you have to kind of take the silt out, and therefore, there is a lot that goes into the foundation engineering of a dam. So, that is the first aspect, and then the other aspect is you need to have some kind of a power station next to this dam and extract energy out of it. So, all this involves knowledge of fluid mechanics and its application to engineering. I am an aerospace engineer myself, and this is one of the marvels of engineering. An airplane, such a heavy machine, it flies, and as you can imagine, it uses these wings to generate lift. So, that kind of counters the weight of the aircraft, and it has these 4 engines. There could be different kinds of engines, and you need to burn fuel in them and generate some kind of a thrust to push the machine forward. So, as a fluid mechanicist or as an aerodynamicist, you would like to know what is the lift that you need to generate on this aircraft. So, what should be the design of the wings to generate that lift, and also in terms of the engines, how much energy does one engine produce, so that you can counter the drag. Now, you see, this estimation has to be done very carefully. If you do not know what the drag is on your aircraft, the air resistance, and you would make an estimate, if you make an underestimate, then of course you would end up putting engines that actually will not do the job for you. But if you put very heavy engines, large engines, then of course your airplane would become so heavy that it would not fly at all. So, a perfect estimation of these forces is very vital to aerospace engineering. You can also see what the airplane does. So, you can see these wingtip vortices which come out of the aircraft, and here is a model that kind of we use to analyze them. We will talk about it later in the course. In fact, you can see that this one aircraft produces these very large vortices which affect flow in a very global sense. So, it is not a very local phenomena, it is a fairly global kind of a phenomena. Sometimes you would like to slow yourself down, not just fly at a large speed, and here is another example, a parachute. So, there is this paratrooper who probably has been ejected from an aircraft, or maybe he is doing some kind of skydiving, and he just opens a parachute and would like to achieve a terminal speed which is small enough that when he lands on the ground, it is safe to take that shock on his legs. So, you would like to design a large enough parachute which actually would slow the person down sufficiently. But you would also like that these lines should not tangle, because if this guy is falling down and this parachute is spinning, that is no good. So, you would like a stable parachute. So, you can see there are some holes kind of structures which are given in this parachute. So, again that requires an absolutely nice understanding of the fluid mechanics, or as you would say, the aerodynamics. Well, it is not just flying structures, I mean even in bridges. So, here is an example of a disaster which happened because of wind loads. So, here is a bridge over one of the rivers, the famous Tacoma Narrows Bridge, and in fact there was on one of the days when it was very windy, this bridge started developing oscillations, and people who witnessed this, they have written accounts about it, that these galloping oscillations, as we call them, they became very large, and eventually it led to the bridge breaking down. In fact, those of you who have a good eye, you will notice there is a car which is still stranded on the bridge, and in fact there were two dogs or maybe one dog with the owner in the car, but fortunately there were no fatalities, everybody was saved. But this has become a landmark that you could have some kind of a flow induced oscillations. Another example of this is the cables, the electricity cables. So, cables that carry electricity maybe over a long distance, they have this kind of a catenary structure, and then when you have wind blowing past them, you could get some kind of an unsteady flow on it, and they can start oscillating, and perhaps they can also fail. This is a picture of our body, as you would be able to identify the role of the red and the blue colors. So, that reflects the pure and the impure blood. So, biofluid mechanics has become extremely relevant, as many of you would have probably seen. So, if you want to have a healthy lifestyle, you would like to know how much exercise is required to actually have a blood flow that does not lead to buildup of some kind of plaque or some blockages in your arteries. So, you can do simulations, you can do modeling to find out how does the heart work, and it pumps efficiently the blood in your body and brings it back. Those of us who would develop some kind of a disease, the heart is not pumping enough, the doctors may say, well, your arteries are blocked and you need to put a stent. So, where should the stent be located? Okay? What should be the diameter of the stent? What kind of a material should I be using? So, that kind of analysis is also allowed these days, very patient specific. Some people may have to go through a bypass surgery. That means one of their arteries is blocked quite a bit, and then just like you build, so if you have a drain that is blocked, you build another drain to bypass the water. So, you can do the same thing. So, the surgeon would kind of bypass a blockage, and you would not want to make that decision on the operation table in the theater. You would like to do that a priori. So, it is possible these days that I could get admitted to a hospital, they run checks on me and they find out where the blockage is, and they can recommend to the surgeon that, hey, if you do a bypass at this kind of a location, then that is best for the patient. How about an artificial heart? Okay, so, somebody needs to put in a brand new device, and you need to understand the fluid mechanics for these devices to be robust, they should perform for a long time, and of course they should require minimal energy, because you need to recharge these batteries and the patient would be carrying these batteries with them. Respiratory system, this has become extremely important in today's context with COVID-19, where some patients would develop some problems with their lungs which don't function in a manner they would function in a healthy person, and then they are put on a device which kind of aids the lung in breathing. So, so you need to know principles of fluid mechanics to run a ventilator. Dialysis, okay. So there are patients unfortunately for whom the kidneys will not work as well as they should. So they are not able to release the toxins out of their body, and therefore they are put on a machine. There are many kinds of machines, you know, you could put some kind of a needle, take out the impure blood, pass it through this machine and put it back into the body. So there are many kinds of dialysis machines, and of course that would also require knowledge of fluid mechanics. Drug delivery, okay. So I have, let's say, an ailment, maybe I have a headache, okay, but I don't put the pill in my head. I mean, I swallow it, right, and then it goes into eventually my bloodstream, and then the bloodstream would deliver it to my head, but it actually delivers it elsewhere. So how much drug I need would depend on my body weight. It also depends on how fast my metabolism is, how fast, how efficient my blood flow is, and so on. So again, that's a big area that requires knowledge of fluid mechanics. You must have seen pictures like this. So there are some advisories of you know, COVID, that when you go out it is safe to wear a mask. And this is a picture from one of the famous companies who do flow diagnostics, and they have produced some brilliant pictures on what happens if you do not use a mask. So they are visualizing this flow using density gradient based some graphics. So if you can see, this person is breathing, so all his air that comes out of his lungs and the throat, you know, that creates a very big signature. On the other hand, if you use a mask, then it is very local, okay. So you could do this kind of an analysis as well, okay. So if you want to do your laundry, okay, you want to wash your clothes, and you want to design a good washing machine. So the idea is that you have dirty clothes, you put them in a washing machine, and you should use as little water as possible, because that's a resource these days, and you want to use as little time as possible, and you want to use as little energy as possible. So what are you going to, how are you going to design a machine that gives you the best possible laundry, okay. So the idea is that you want extremely good agitation, okay. So you have put some detergent, and that detergent now has to go and act into the dirt and kind of push the dirt out. So you need to have some agitation. So here is an example of a motion. So you would do weak motion in one direction, strong in the other, and create some vortex structure, and that's how you would have an efficient washing machine. How about sports mechanics? Okay, so I am sure there are lots of you who are sports enthusiasts. So I play badminton myself, and I am interested in finding out why would the trajectory of a duck feather shuttlecock be different than a synthetic shuttlecock. What exactly is the flow? So it turns out that through these gaps in the skirt, the flows goes in, it forms some vortices, and that in turn affects the forces on the shuttle. Swimming, okay. So I want to be a good swimmer, and I am told I should do certain strokes. But what is the best way of doing the strokes, okay? Well, here is a team that would like to win an Olympic medal, and then the coach kind of visualizes what they are doing inside the swimming pool, takes pictures, does CT scans, computes the flow around them, and then in fact even kind of advises them that should I keep my fingers closed, should I keep them slightly open, what is the added mass when I take a stroke, what is my hand position, am I flipping my legs properly, and so on, because I would like to splash the least amount of water and get the maximum thrust. Here's a cricket ball, and I am going to actually give you a lecture in one of these days when we have learned a little bit more that what causes the swing, the reverse swing of a cricket ball. Okay, the age old question, can a new cricket ball reverse swing? Okay, we hear that the ball has become old and it is reversing, but can a new cricket ball swing? What is the role of seam? What about a red cricket ball versus a pink cricket ball? Okay, what is the effect of humidity if the seam kind of gets swollen up because of moisture in the air? So all that you could actually understand using fluid mechanics, and I am going to actually show you in a lecture about some of the work that we have done. Many of you may be interested in cycling. So again, I am a sports enthusiast, and suppose I want to do well in some kind of a meet, an athlete meet. So the question I want to ask myself is, and I ask my coaches, that who encounters more air resistance, the guy in the front or the guy at the back? Okay, so in the sense that if I am going around in a race, okay, on a circuit, am I better off following somebody for most of the race, or am I better off in leading somebody in the race? Who has more drag? Okay, so you can actually do these calculations. Okay, so here is a fluid mechanics calculation which would exactly tell you what is the resistance this biker faces, what is the one the person behind him faces, and so on. Soccer ball, we are all aware of the legendary swing of a soccer ball. So all that can also be analyzed. In fact, as you know, Adidas comes up with new models of soccer balls every few seasons, and they try to make the sport more exciting. I am sure many of you are interested in Formula 1 racing. Okay, this is again a magnificent machine which actually pushes technologies to the limit. So many of you may be aware that a lot of car companies, they spend enormous resources in actually getting good machines, and then some of these technologies, the spin-offs, they come into our regular cars as well. Amazing aerodynamics in the sense of the nose cone structure. So you are actually going at very high speed, and you want very little drag, and you want control. So what is the design of the nose cone? Air intake. So here is an air intake. There could be some air intakes in the cars on the side. So how do you design air intakes that you get maximum volume flow rate inside the engine of a car, but at the same time the drag it offers is low? Okay. There are actually these wing-like structures, sometimes they are called as spoilers on the racing cars, and you may or may not know the reason. The thing is, these cars are going at extremely high speed, and when they take a turn, okay, they can actually fly away. So you want to increase the friction, and as all of you know, the force of friction is directly proportional to the coefficient of friction between the tire and the road, and also the normal reaction on the car. And the normal reaction is proportional to the force that the car exerts on the ground. So what the designer does is, they put wings which are actually going to, so these are like reverse wings. So in an aircraft the lift is upwards, in a car the lift is downward. So I have more downward lift, so in fact the car actually feels heavy, so I have more friction, and therefore I can turn at much larger speeds than I would if I did not have these reverse wings. In fact, you will be amazed that these spoilers these days can generate so much of downward lift, they can actually fly inverted on a roof. So in principle, this room in which I am sitting, a Formula 1 car could actually run upside down on the roof. Very exciting. Okay, so these were some of the applications that that should excite you about why you should study fluid mechanics. Okay, and of course the related heat transfer as well as the mass transfer. I now want to shift the attention to some flow phenomena, okay, that at least I find very exciting, and sometimes they are even counterintuitive, and I would like you to enjoy this gallery of motion. So I have taken these pictures from Professor Van Dyke's book, An Album of Fluid Motion. So I have not given the credits on each slide. I thought I would just put them up front. So most pictures are taken from this book. If you get an occasion to look at this book, I strongly encourage you. So we start from the very basic, okay, flow past a circular cylinder. Okay. It's the simplest possible configuration to study a flow. Why? Most other shapes would be complex, okay, they have more geometric parameters. The simplest shape is a circle. There is only one geometric parameter, and that is the diameter of the circle. No sharp edges, extremely smooth. So I would imagine that the flow past a circular cylinder should be a piece of cake. Everybody should be able to guess what happens. Wrong. Actually, it's extremely rich. Okay, it's so fascinating. I hope I can convey that in the next few slides. So we define something called a Reynolds number, and I am sure you have studied that in your class 12th. So Reynolds number is, as you remember, density of the fluid times the length scale, which in this case is the diameter, times the speed of the flow, and divided by the viscosity of the flow. Okay? It's a non-dimensional number. So Reynolds number can be thought of as a non-dimensional speed if you fix the diameter, if you fix the medium, in this case it is the air. So if I increase the Reynolds number, I get, it means I am talking about a increased flow speed coming into this domain. So this is a picture at extremely small flow speed, and the flow has been visualized by using aluminum powder. So you sprinkle aluminum powder, and then when you take a picture, these little particles, they reflect light, and you can actually see what the flow looks like. So you can see the flow is symmetric about the x-axis. In some sense it is also symmetric about the y-axis. So it is enough to look at the flow only in one quadrant. You can see a trace of a flow bubble being formed here, which is actually more clear if I increase the Reynolds number. So here the Reynolds number is about 10, and here it is about 13, and you can in fact see there are some vortices, standing vortices as we call them, they appear. Standing in the sense that they just stand there, just like you talk of standing waves in physics, you can talk of standing waves in fluid mechanics. So there are these little eddies which get stuck there. So fluid particles go not only around the circular cylinder, they even go around these eddies, and the flow in the eddies is, they just keep going in circles. And then if you increase the speed further, let's say about 26, then these eddies become larger in size. Okay. So far what has happened, I had a uniform flow coming in, and with increase in speed I get these two standing vortices which seem to increase in size, okay, as the Reynolds number increases. Okay, let's see what happens at higher Reynolds number. So this is 28.4, and now you see bigger vortices. Okay. Now I wanted to show this picture because again the way the picture has been visualized is very commendable. Okay. So what has been used here is condensed milk. Okay. So condensed milk has been used to find out what is the motion of the fluid particles. Okay, this is Reynolds number 41, this is the diameter of the cylinder, and you can see this is the length of the vortices. Okay, so they are far bigger than the body itself. And now something interesting happens. You have these two vortices. If you increase the speed further, both of them are trying to grow, but as would happen, one of them wants to acquire more space and would try to elbow the other guy out. And this is in fact what happens. If you increase the speed any further, then one of the vortices, because of some reason, becomes a little bit larger and tries to push the other guy down. Okay? And let's see what happens. There you go. So when you increase the Reynolds number larger, actually those vortices become larger. So when the upper one becomes large, it becomes so large that the flow cannot hold it anymore, so it is released. Then the lower one starts increasing in size, then it becomes very large, it is released. So you get vortices released from upper surface, lower surface, upper surface, lower surface, and they start convecting downstream. Beautiful. So what is happening? You in fact have a uniform flow coming in, which is not changing with time. Okay, it somehow separates, and I will explain this term, what is meant by flow separation. And then you see that the flow downstream of the cylinder, it becomes unsteady in time. So it starts changing with time. Beautiful. So you had a flow coming in which is steady, and then the flow downstream which is unsteady. And in fact, you will see now you don't have a symmetry about the horizontal axis, which means that now the force on this body is going to change with time, because the symmetry is, I mean, some of the location of these vortices is changing with time. Okay. So vortex shedding will lead to unsteady forces on this body. Sometimes it feels a force in the positive direction, and when the next vortex is shed, then it feels a force in the negative direction, and so on. Okay. So to sum up, I had a flow that comes in which is steady, and now I have a wake which is unsteady. But the good news is the flow is extremely periodic. Okay. That means I can watch it for hours together, and it just keeps repeating after. So this phenomena which, so if I drew a section here and I observe what happens at this section, it is extremely periodic in time. The same set of events keep repeating time after time. Doesn't happen at very high speeds, which I will show you. Okay. This is an example just to tell you that just like for a cylinder you had vortices which were very strong, but if you had a body which was more like an ellipse, okay, so now you see these vortices are there, but they are a little bit weaker. So they are there for thin ellipses also. What happens when I increase the Reynolds number? The nice periodic flow that we saw earlier, now you see it becomes so complicated. Okay. So this is at a Reynolds number of 2000, and this is at a Reynolds number of 10,000. And this picture is particularly fascinating. So you still see the big vortices. Okay. These are the big vortices, and in addition you see tinier vortices. Okay. There are extremely small vortices. So you have large vortices, you have smaller vortices, and now you are getting into something called a turbulent flow. So we are going from a laminar state to a turbulent state, wherein in a laminar flow you had, kind of big vortices which were very periodic, but in a turbulent flow now you are going to get a family of vortices. Okay, they coexist at the same time. So I have a large vortex, and then I have these many smaller tinier vortices. Okay. So this is a fascinating flow in the sense that I have a flow coming in which is perfectly uniform, steady, and the flow downstream of this object has become unsteady. Okay. And why did it become unsteady? Well, we will talk about it later. It's essentially because of the steady flow is unstable. Okay. So therefore it kind of becomes unsteady. And now you have these big vortices, smaller vortices, and this part of the flow leads to much heavy mixing. So I go back to the example of the washing machine. In the washing machine you wanted heavy mixing, you wanted to agitate your clothes so that the dirt just flies off. If you want your washing machine to do well, you don't want laminar flow there, you want a turbulent flow. And here we have an example that this flow is laminar, it's a very nice organized flow, and this flow is now getting more turbulent. Okay. The flow very close to the body is still laminar. Okay. And I will show you some slides that as you keep increasing the Reynolds number, even this flow can now become turbulent. Okay. Just to show you that the shedding of these vortices is kind of universal, these are two pictures. So there is a flat plate, it is not a cylinder anymore, and this actually is a ship. So somebody has taken a picture of a ship in which there is an oil spill and there is an ocean current, and then the oil spill is kind of giving you, they are acting as flow visualization markers, and that gives you the idea of vortex shedding. And again you see very nice turbulent structures between a well organized vortex shedding. Okay. So this should give you an idea about how complex the flow is. Okay. The incoming flow very quiet, okay, uniform, but the flow downstream of this object completely changes it. All right. Now let us see what happens close to the body. So it's the same circular cylinder, and we are now talking about very large Reynolds number. So this is a relatively small Reynolds number, this is a relatively large Reynolds number. Okay. This one you will see, this we call as the boundary layer, and we will discuss this later in the course, what is a boundary layer. But you would see that this boundary layer is extremely organized. So you can imagine if you are riding a motorcycle and you go on a curve, okay, you can negotiate the curve if you go at a relatively small speed. But if you are very ambitious and you try to negotiate a curve at a large speed, you kind of fly off, you separate from the curve. Something like that is happening here. There is a fluid particle which is trying to negotiate this curve. In this case, it is a geometric curve, and then at some point it separates, okay, and that is what is happening here. But you will notice the flow is extremely organized, so we call this as a laminar boundary layer and the separation as a laminar separation. In the lower picture, the inflow speed is larger, and what you would see is that now the boundary layer has actually become turbulent, because here you were able to see there was almost no mixing, it was very organized, but here you can see that there is enormous mixing inside the boundary layer, and as a result it is able to supply the energy from outside the flow inside the boundary layer, and it separates a little later. So this flow separates somewhere here, whereas this flow is separating somewhere over here. Okay. So more mixing and separation is delayed, less mixing, separation is earlier. It has extremely big implication on drag. In fact, what people see is that if I was to calculate the air resistance or the drag on this body, it is large, and as soon as the boundary layer becomes turbulent, if I go to a large speed, then actually the drag becomes smaller, and that is known as drag crisis. We will be talking about that in the course. What happens now if in addition to this smooth surface you have a corner? Well, the separation point for this corner is somewhere here, but then if you have a turbulent boundary layer, you can see the flow stays attached. How about a sphere? So that was a two-dimensional body, a circle, but if you have a sphere, then this is a laminar boundary layer which is separating, and you can see very nice separation of the flow and then the wake downstream. But the wake is quite wide. Now if I go to a turbulent boundary layer, so I increase the speed, now you will see the wake has reduced in size, there is a lot of mixing going on. Okay, so you can see that the smoke here is a little bit, I can see through it, okay, it is a little bit more transparent, and here I have lost the transparency, it has become more translucent because there is heavy mixing inside the smoke. So the boundary layer here is turbulent, and the separation is much lower, and you get a much narrower wake. Okay. In fact, I can ask you a question which you could answer just from intuition, that which of these two bodies would have less drag, and intuitively I would pick this one. This should have less drag, because when I pull this body through the flow, the one with the laminar boundary layer disturbs the flow a lot more than the one with a turbulent boundary layer, and therefore because this disturbance is large, somebody must be supplying the energy to the fluid. So I am transferring, so if I pull this body, I am transferring the energy from the body to the flow outside. It is larger here and the transfer is smaller here, and therefore it has smaller drag. In fact, when I design a car, a sports car or a sedan, I would like to disturb the flow as little as possible, because if I energize the flow outside the car, it must be coming from somewhere, and it eventually comes from the fuel that I burn inside the car. Great. How about bodies of interest in aerospace engineering? Okay, so something like wings. So here is a long tapered body, and you can see there is no flow separation here. It kind of just hugs the curve and stays very nicely attached to the body. And I have already shown you this picture for a cylinder where the flow separates and it gives rise to all kinds of interesting flow phenomena. So this type of a body we call as a streamlined body, and this body which develops a lot of flow separation and therefore enormous amount of drag, they are known as bluff bodies. So you can see I am an example of a bluff body, but a sleeker athlete would be a streamlined body. So if I run, I will generate more drag, but a sleek person runs would generate less drag. And that's what is written here, that drag in a streamlined body is going to be much smaller than drag in bluff body. And I want to show you some examples of how you can use streamlining to actually reduce the drag. So suppose I had an initial body, okay, in which the dimension, the vertical dimension is t, and I want to reduce the drag on it. So I have drawn some stages which I will show you. So the first step I could take is I can just add some kind of nose to it, so that the flow which was separating here, now it does not separate and it gets a little bit delayed. Okay. So right away the drag will reduce by 45%. So you must have seen trucks on highways. Okay. Sometimes the trucks will put a canopy on top of the roof. In fact, it is very helpful because that would reduce the drag and without really doing much. Okay. Now what I do is, in addition to just modifying the front part of this body, I actually add a long tapering tail at the end, and let us see what happens. There you go. Okay. So the original drag was F, now you have less than 10% of that drag. I mean it's very little. And just to give you an idea, if I took a bluff body of 10% the size, okay, it generates the same amount of drag. So if I look at the spoke of a cycle, the spoke of a cycle has a circular cross section. It generates enormous amount of drag, okay, and it has the same drag as compared to this very large streamlined body. We will talk more about this, but just to give you an example, nature sees a lot of streamlines. So if you look at fish, you look at some mammals, for example, dolphin is highly streamlined, and in fact it has some special things on its skin. Shark has some special things on its skin, and they have very little drag. This is a car which kind of illustrates that you can use streamlining to reduce the drag, and of course we use airfoils for wings. How about bicycles? So here is an example of a design where I would like to use my knowledge of fluid mechanics to reduce drag, okay, and these are some of the attributes. So first thing is, I would like to reduce the frontal area and the flow should go smoothly over me. So therefore I would make the handles so that I am forced to stoop, okay. So I must have a stooping posture that the flow kind of goes over me very nicely. So that is the drooped handlebars. The helmet. So there is a helmet that you need for safety, because if you fall down you should not get a head injury, which is very dangerous. But then you also append a streamlining effect to it, so that the whole body becomes a one body and you have little drag. Notice the wheels. We would actually like to have solid wheels. As I showed you in the previous slides, spokes generate enormous amount of drag. So you have covered the wheel. You cannot cover the front wheel because you need to turn it, and then when you turn and if you make it solid, then it is going to generate some side forces and that will lead to stability problems. Instead what you do is you make this diameter shorter than the rear wheel. In fact, even the spokes you can engineer them so that the cross section is not circular anymore and you get less drag. And likewise all these frames, they are not just raw pipes with circular cross section, they are very nicely streamlined to give you as little drag as possible. Something about turbulence. If I take a tap and I increase the volume flow rate of the water, then at low volume flow rates I get a jet like structure from the tap, and it almost looks as if it is made of glass. I can see through it, okay. So that's laminar. But if I increase the volume flow rate even more, now the water will come out gurgling from the tap, and in fact it would entrain water from the side and you would get lot of air bubbles like this. So this is a laminar jet and this is a turbulent jet. Okay, we are going to study more about this in this course. I thought you may enjoy this picture, so please take a moment to see if you can identify what this picture is. In fact, it's a propeller. So if you look carefully, these are the blades of a propeller, and the propeller is spinning. Okay, and then at the edge there are these very nice vortices. Okay, so this was just to tell you how interesting the flow is. In fact, if you look at the flow around a ceiling fan or even a table fan, you get these very nice vortices, and we'll talk about it sometime later. They also lead to some noise, which when you run the fan at a high speed, you can see that there is noise because of these vortices. So vortices released from one blade could actually hit the other blade in a ceiling fan. We'll talk about that. Here's another beautiful experiment that was conducted. In fact, people who smoke do this very often. So I am not advocating smoking at all. I don't think smoking is good for health. But those who smoke probably try to make smoke rings. And if you make two smoke rings in a succession, they do some very interesting dynamics, which in fluid mechanics is called leapfrogging of vortices. So here is an experimental setup where you have two smoke rings being generated, one after the other, and there is a caption here which you can read when you find time. And then what happens, this ring which was released earlier kind of increases in diameter, and this one which was increased later, it reduces in diameter and it goes through, so it leapfrogs. And this is happening because of the velocities induced by these vortices. So these vortices, they induce a velocity field, and we'll look at that in this course. So you see the first leapfrogging, and now this guy who actually was released later has now gone ahead, and now this ring starts increasing in diameter and this ring starts reducing in diameter, and again because of the induced velocities, the front one slows down and the one at the back, it increases in speed, and they leapfrog once again. And therefore you would have this very nice situation where you release two smoke rings one after the other, and they keep leapfrogging. Okay, so it's a very nice scene. You can probably even find some images on YouTube. Some more pictures of vortices from a wing. Okay, so here is a wing which generates lift, and some of you may know why a wing generates lift. So you have suction on the upper surface, and on the lower surface you have high pressure, but then at the wing tips the air kind of spills over. Okay, it goes from high pressure to low pressure by spilling over, and that actually generates these vortices. Okay. Here's another very nice picture which is the flow on a spinning disk. So those of you who still use the old hard disks, not the flash drives, okay, you may realize that a hard disk actually has a magnetic material which stores the information, and then there is a head which moves on the hard disk. Okay, but the distance between the head and the hard disk, the spinning hard disk, is very small. Okay, and the faster you spin the disk, the quicker you would read the data. So there is a spinning disk, and then there is a head which kind of moves in the radial direction, and that is how you read a hard disk. Now the problem is that this flow goes through a transition. It goes from a laminar state on the inside to a laminar state on the outside. So what is shown here is simply a turntable, and on the turntable there is fluid, and now you spin the turntable. Okay, and what will happen is that the speed of this fluid is larger because it is moving with the turntable, and this speed is lower, and you get this very nice instability where the flow here is laminar and the flow outside is turbulent, and you get these spiral kind of waves. And a similar thing happens in a spinning sphere, and you can see if you had a spinning cricket ball, for example, you would see these very interesting instabilities. This is another instability which we will talk about in the class, which is called the Kelvin-Helmholtz instability. So what has been done here is that there are, so I will read the caption for you. There is a long rectangular tube as shown here, which is initially horizontal, and it is filled with water above colored brine. So you put salt water, and then on top of it, then these fluids are allowed to diffuse for about an hour, and you quickly tilt it by 6 degrees. So the brine, it accelerates down the slope and the water accelerates upward. So you get some kind of a concurrent moving flow. So the flow at the top moves that way to the right, and the flow at the bottom is going downwards to the left, and because of that you generate some instabilities, which are these fascinating structures. Okay, people have even seen them in clouds. All right, I hope I have been able to convey to you in this opening lecture how interesting the fluid phenomena is, and what are its applications in engineering, and as well as in understanding the science behind these flows. And hopefully you would now be motivated to actually look at the details in these flows and understand them. So thank you very much.